Yeah.
All right, let's get started. So we'll have some announcements. Exam 1 grades have been released. We'll go over that, some of the grades in a second. Homework is due Monday. I have office hours that day as well. Next week, we're going to start kicking off the project. And so you need to go through and do ideation slides. We'll go over those in a minute. And team formation. So those are dates to keep track of. This is a required event. So thinking about the exam, these are the grade distributions of last semester and the 2 exams that you guys looked at, okay? I know that these are pretty low grades. I promise you, we curve the class. Just because you got a grade that's an average here doesn't mean you're in any trouble at all, okay? We can look through this. You may have probably already seen in your emails, but who thinks that this year's test was harder or easier than the practice exams? How about easier than the practice exams? A couple people. Harder than the practice exams. Okay. Well, the statistics don't necessarily bear that out, but you know, a 2-point or 5-point difference isn't significant, I would say, as a measurement method. But I would say it's about as challenging as the previous exams. I will say that the last problem took more writing than we had really appreciated how long it would take for you, and we tried to grade accordingly. In the future, I would probably make that last section a little simpler. But you can see that some people did particularly well, so I say we got to the upper end. Most people are here kind of what the class average is. And there are some people on the lower ends. I would say let's talk and make sure that you're understanding in a good position to be successful in the class. I think everybody should be able to pass this class, even if you don't do well on an exam, because what I'm really looking for as an instructor is for you to demonstrate to me that you know the knowledge of the course. And that doesn't have to be just through an exam. It could be through other methods. The project is a great way to demonstrate that you know the knowledge of the course. People learn in different ways. So any questions about grade distribution or grading of the exam? In general, yeah.
Posted.
Solutions are posted. Yep.
Okay. To the solutions.
You don't think you have access to the solutions?
When you go to open it, it says you need access.
Okay. I thought, but the folder I put it in should have already granted access, so I will double check that. We have a little break. Okay, any other questions? Yeah? All of them were single answer, yes.
How helpful will the curve be?
I don't think anybody when you get all the way through the class will be surprised by your grade, okay? Nobody is going to be like, oh, I understand embedded systems way more than my grade demonstrates. So I rarely have people surprised. Don't worry. The other way to say it is don't worry, I got you, okay? What else? Any other questions? All right. So regrade request, I don't think I have it on here. We'll give you a week. I think they're due not Friday, but next Friday. So try to give you a deadline to do your regrade requests so that we have a single time where we're going to go through them all rather than doling them out through the semester. That's usually pretty horrible. Okay. So the project details will be released tonight. The first thing you need to do is do some ideation slides. You need to make 3x slides that convey some aspect of a project that you want to do. This is really to force you to think about what is it that you actually want to do. So you need to have less than 100 words. You need to have one image. It can be hand-drawn. It can be GPT generated. I don't care, whatever you want. You have to put it, the slides have to have your name on it to receive credit, and then there'll be a folder for you to drop them into, okay? And then if there's any projects that you're particularly excited about that you would like to present to the class in some way, so in the team formation event, we'll describe the project in more detail. We'll talk to you a little bit about the process, the project, and the support that we give you, and the parts that are available. And then students can come up and present their ideas to try to get other students, recruit other students into their exciting ideas. And so the star is a way to indicate that you were excited about this slide and would like to present it. So the team formation event is Friday from 4:30 to 6:30. We'll have pizza. Attendance is required. What questions do you have?
Sides for one idea or?
Three ideas, one slide each. Yep.
Still?
Yep. I mean, it's just a class participation point. You don't have to kill yourself over it, right? Like, you should go. I'm going to mark if you're there or not, and I'm going to give you pizza. So if you're like, I'm hungry, you can go over to Beister and then we'll feed you. All right, what other questions do you have? Yes, in the back, very loud, please.
After the information, can the project like change?
Yeah,
Okay.
because a lot of things, team formation, the goal is to find people that want to do like projects. And then what's going to happen is you're going to pitch a project to me and Matt and James, and we're going to say like, hey, that's insane, that's cool, but we can't probably do all of that. Or, hey, you might want to explore this technical path. Sometimes through that process of going back and forth with your instructors, the project does change dramatically. But we try to make sure that it's something that is actually achievable and will exercise the core elements of the class.
How many people in your team?
So we're 80, what do you got, 85 in this class? It's a great question. 3 to 4 would be ideal.
Just to clarify, you said we're gonna come up with ideas and present them.
Yeah.
Okay, who's like everyone's presenting one?
No, people who put a star on that thing and are excited.
So everyone makes the slides,
Correct.
and if people want to present, put the star.
Because the act of making slides will make you force your brain to think things. And then you'll be like, I want to do this idea instead of that idea. But if you come in there and don't think about it at all, then you're out like, don't know what you want to do, and you're just kind of lost. So it's forcing you to brainstorm.
Do you have like some guidelines on how complex it should be or how simple it should be?
I'll release the spec tonight. The base goal is to exercise the core elements of the course. So like memory mapped O is going to be pretty easy because you can't talk to a GPIO pen without it. But you're going to have like timers and interrupts and I2C peripherals. So you need to exercise a bunch of these things and then make the real trick of this class is that you have to do the system integrations. Anybody know the YouTuber Stuff Made here? It's great. He goes through this thing, he calls it integration hell. It's beautiful. Oh my gosh. You write code, you hope it works, and it's just an ever-loving disaster, and then you spend 2 weeks debugging it. Perfect. That's what embedded systems is. That's the learning experience I want you to have. You have to make something that really actually works in the real world, and we're going to measure you on that. Yeah.
So is it like at the end of the event we have to like analyze which team we're on, or
Correct.
is it just like get an idea?
You should have a team formed by the end of the event, and then like 3 days later, what is it? Hey, the following Wednesday there's actually a form you have to fill out and say, this is the team I'm on. But hopefully most people will figure that out in the event. What other questions you have? Okay. Yeah, so read through the project proposal. There's a project there. You will make a project proposal, and there's a sample one up there. So read through this. This is after you've made your team. You read through this. You go and make your proposal, and you're going to sign up for a review slot. These are last year's dates, but you'll sign up for a slot to like individually as a group meet with me or James or both of us. I forget how it's going to work, and we'll give you direct feedback, like one-on-one feedback about how your project's like. Give you advice, give you feasibility, tell you if it's complicated enough or if it's too easy, those sorts of things, and help you land on a project plan that makes sense. All right? I did a little out of order, but I'm going to switch back to grading for a second. I'm going to give you the hints about how to get as many points back on your regrade request, okay? You want to get more points. Okay, here's what you do. You could go and say, hey, there's a factual error on my exam, and the grading in my exam. Say, for example, sorry, my handwriting is really messy. I know it's hard to read, but I wrote this, and please take a second look. And then the graders, and me and James and everybody will go and look and say, aha, all right, I caught my error. It's a factual error. You wrote this other thing. Super easy. That's like a no-brainer. You're going to get the points back. The ones that are harder are, I meant to say. Like, I wrote this, but I meant to say that. Like, I meant to win the lotto every week. Right, so that's going to be really hard for us to regrade. So you probably can't do that. I can only really grade what you've written. There's things like a value judgment, right? Where it's not cut and dry facts. It's like, did you explain this well enough? And so those can be hard. A bad example is, can you have more points? I also would like to win the lottery and have points, right? Like, it's just, I want, okay? A much better strategy that will convince me is say, the core question is asking for C, and I demonstrated A and B in my answer, and those are key components of C. Now you have a logical reason, and you're giving me evidence of why I should give you more points. But if you just say, I want more points, probably not going to happen. And another tough one is, the question asks X, and I answered Y. Can I get credit? Well, probably not. You answered a different question. And so to combat this, sometimes we have questions that are confusing or have errors in them. So we go through and systematically, we go through and have multiple instructors read the exam, even though one of the problems it didn't work very well. And we look at the statistics of the questions to make sure there's no inherent error. So unless there is a systematic error in the question, like that is demonstrated by a large population, it's unlikely that we'll change that sort of request. If you answered Y, that's probably the wrong answer. Is this helpful in understanding the psychology of the graders and how you can get as many points back? Kind of? Okay. I think that should be the third. I'm not exactly sure. It was Friday. Okay. All right, so we're going to go on to timers. Is there any logistics questions? Anything else? Yeah?
Will the regrade request?
Oh, you got to go real loud.
Will the regrade request decrease our grade? And will it be graded down?
Rarely.
Okay.
I mean, I have had people that just trying to get every single little point, and sometimes I get a little angry. And then usually what I do is I just push their thing away and I don't answer for 2 weeks. And that lets me cool down so I'm not so angry with that person, and then they're fine. But rarely do I get in a case, I remember when I was taking physics, they'd be like, if you submit a regrade request, I'm gonna regrade your entire exam. We're not gonna play that game unless there's a problem, okay? All right. All right, so we're going to move on to timers. So last we talked about interrupts, and now this is another class of modules that you'll find on microcontrollers. It's a fundamental model, basically, is measuring the passage of time. So most of today is going to be talking about the timer modules you have. Later on, we're going to talk about SysTick, which is a specific timer built into your core that's required by ARM, and that's what they would use for an operating system. So your device does support an operating system in the context of an advanced scheduler. And then finally, we'll talk about virtual timers. You probably won't get to these today. We'll get through this, but that's what's coming up. If you're looking for readings, so let's see. So this is from the developer's guide. There's an entire developer's guide on a reference for your STM32. So you can look through those. If you're looking at the book that we recommend but don't require, chapter 15 is pretty good. And STM has YouTube tutorials that they professionally made. They're a little bit more tutorial rather than educational, or rather than, classroom teaching, but they're pretty good. So there's some other resources. If I don't make sense to you, Matt doesn't make sense to you, James doesn't make sense to you, other resources. All right, so a little background. So timing, right? There's a bunch of different functions that you want your embedded system to do. So thinking through how does your iPhone work? So you have world time, you explain time zones, you have things that alarm, so things happen at a certain time. You have stopwatches that measure the passage of time, and timers that can count down to 0. So these are different functions for manipulating time or counting time. We also use timers to control things. So we talked a little bit about how timers can control a servo by doing something called PWM. You can also have DC motors we'll talk about, and RGB. So now the idea here is microcontrollers are really good at measuring and controlling time. They're bad about just about any other real-world interface, like analog they're really bad at, or even delivering power they're not that great at. But they're really good at controlling time, and these are all electrical ways to control the external world through timing mechanisms. So we'll talk about how to achieve that. So let's see. We have timers. Kind of review here. Periodic. What do I want to say? So you could have an interrupt go off that causes you to do a task periodically. So maybe every second you want to go through, or maybe 500 milliseconds you want to go through and check a bunch of sensors to see if some event has occurred, or you just want to log some data. You could just be in a while one and just every time you go through, check that sensor, but that might be a little chaotic, especially depending on code execution, and maybe you want a really good time base. You want to measure the sensor value every so often. So one thing you would do is you'd set up a timer that sets off an ISR, so in that interrupt, you'll do the task of measuring those sensors. So now you have very precise measurement of time. You can provide you like accurate delay loops, generate pulses and waveforms, measure the duration of time, and then know that this is actually a fairly challenging one we'll talk about. You have to measure the passage of user time, right? Like, how do you display and keep track of months, days, years, minutes, hours, seconds? Like, that sort of conversion is not inherently, well, microcontrollers are good at counting microseconds and nanoseconds. They're not good at measuring long periods of time that humans care about. Okay. So here's a question for you. How do electronics detect the passage of time? So let's think about how do humans do it. How do we do it as humans? If we say we didn't have a clock, we have to go look at the natural world around us. That is our method for understanding the passage of time. So humans could look at the rise and fall of the sun. You could have a mass spring mechanism, right? So like old school clocks that you could use to measure the passage of time. So the question for you is, how do electronic devices measure, like at the physics level? How do they know how long time has passed? When you take 60 seconds, brainstorm with your neighbor, come up with an answer. How do they do this?
I was wondering. So if you just
No, they use an oscillating crystal. Little crystal that oscillates. That's exactly it. No, I'm not. I don't
That's it. It is done.
Me too. I got to the last question. I realized I'm like, I spent too much time.
Signal sky, transfer. Escape.
Short answer. I lost points on that too.
All right, what do we think? How does an electronic device measure the passage of time?
Is it like a piece of quartz that vibrates?
Okay, it is. Fantastic. Anybody else want to come up with an answer? That was perfect. Yeah.
Like a 555 timer, for example, it uses a specific resistor and capacitor combination with a known time constant.
That's true. So RC time constants have, I guess you have to have some constant in that circuit that has a known voltage, which is fine. So you take a known voltage and you can use the decay of that known voltage through an RC time constant to create a time base. All right, 2 methods. Forgot about that one. It's great. Any other methods? Ooh, you could. Nobody does that. But capacitors are just the inverses of inductors. They're vice versa. So we can construct a circuit that would have an LC time constant, or an LR, sorry, an LR time constant. It's just complicated to make. That's a good idea. Yeah.
I mean, like on a broader scale, like for like global time, I think they like ping satellites, right?
How does a satellite know what time it is? Gotcha.
Isn't it like atomic? Like no, never mind. Actually,
No, there are atomic clocks.
yeah, atomic clocks. I just didn't know how they worked. So I didn't want to talk.
Basically, how do atomic clocks work? How can that be a hole in my knowledge? I don't know how. Well, I don't know how to build one. I know how they generally work. I think it's like you get some helium or something and you get it to a known temperature and you put a wavefront through it and it oscillates at a certain time. I don't know, I have to go look that up. That's fantastic. I didn't know something. Okay.
So you said like the original answer was like oscillating quartz, right? Do you have to like calibrate that ever?
Yeah. Okay, let's go on. You got it. You're getting to it. All right, so let's start off with anatomy of a timer. So first we start down here and we're gonna go through the oscillating quartz and the different types of thing in a second. But we have some physical external things. So these are supposed to be I/O pins, and you have an external crystal or an external oscillator, something that's keeping track of time for you. And then you have to turn that into basically square waves. You have to have a clock drive or something that's going to turn more or less this analog thing into structured clock, and then you can pre-scale that, manipulate it. We'll talk about all these things in a second. There's a counter that keeps track of the passage of time, basically counts how many little clock ticks have gone by. We can do things like what we'll learn about today. It's these capture and compare modules that allow you to manipulate the start and stop of the timer. And all this is essentially written in assembly. I mean, you will write this in C, but this is, I'm trying to denote that this is low level, or where it says in Verilog, but low level hardware interfacing. And then you go up the stack a little bit and you have your system level, and then I guess you get into assembly. And then at the abstract level, right, where you're actually making the thing that shows the user, where it's like a clock interface, then you're getting to C. Okay, so let's start with the lowest level, crystals. So a crystal is a fundamental electronic component, just like a capacitor, resistor, and inductor. It is a piece of quartz that when you strike it with electricity, it will only let certain frequencies of electricity through it. So you can imagine that this is a very narrow band filter. And if you set it with a low frequency through here, it would not pass through. And if it's too high, it won't pass through. So we consider this like a band pass filter. It's super, super narrow. It's one way to look at it. And then you have this inversion circuit here. So this is like what's inside your microcontroller. Again, this is not important that you know exactly how the circuit works. Just know that there is a circuit. So this is the line between your microcontroller and your circuitry. And on your boards that you have in class and lab and anything that I've ever made, you put a crystal on here that's tuned to a certain frequency. You have to put some loading capacitors on here. The manufacturer of the crystal will tell you what these need to be, and you have to kind of check the data sheet to make sure it's all about the same range. And then this is an inverter that causes a negative phase. So you get 180 degrees out of phase and it will start oscillating back and forth. So any energy that starts going through here, some of it will get through and it'll oscillate back and forth. And basically the whole output of the circuit will be precisely tuned to the center frequency of that circuit. And there's some painful startup stuff that you don't have to worry about. You just have to know that your embedded system is going to need an oscillator or a crystal oscillator, and that you have to put capacitors on there. So there's a wide range of crystal oscillators. They are pieces of quartz, and they come in different sizes. So these are like old school metal cans here and here. These are good. They're fairly large, but they have good EM suppression because they're in metal. These are kind of more modern ones where they're small, like, I don't know, this would probably be 1 millimeter by half a millimeter. Maybe this is 2 by half, that size. And then here's another one in a different type of package. And these, again, oscillate back and forth. And the trick is that you can go buy these in a wide range of frequencies. So they're not tunable per se, but you will go to a place like DigiKey or Mauser, and you can choose one that has a certain frequency. So a classic one is 32.768 kilohertz. It just happens that as you multiply that out, that translates to seconds, hours, and seconds, minutes, and hours very well. So you can get seconds out of by multiplying that up with a counter. So that's a very popular one. But crystals are generally good for low frequency things. Yeah.
Quartz or is it like easier to access?
Well, best is a funny term in the engineering world because best means like, is it cheap? Well, quartz is pretty cheap. Is it functional? Like you have to balancing all these sorts of things. So it's maybe not the most pure tone in terms of frequency, but it's cheap. You can buy one of these things for less than a cent, and when you buy in bulk. So if you go up the food chain a little bit, you get to SAW resonators. So this stands for surface acoustic resonators. This is a piece of silicon, basically, that has a structure on top where you launch an acoustic wave across, and it has a certain propagation delay. Again, the details are not that important. Sometimes they're called ceramic resonators. But these typically go into 10 megahertz up to 100 megahertz. So these are good for clock sources for like your main clock on your device would be from one of these, while the quartz resonators are good for like low frequency stuff. And interestingly, there's kind of like this gap between 1 megahertz and 10 megahertz where there's not a lot of good resonator options. But yeah. Anyways, these are relatively frequent, relatively stable, good frequency consistency, but that you pay more for any of these devices if you want the parts per million of the frequency shift to be smaller and smaller and smaller. And then there's also temperature coefficients that would be a problem. Yeah, and so you have, I guess I forgot to throw this before, on your boards there's a specific input port for 32.768 kilohertz. They want this, your board is looking for precisely this crystal because the rest of the system depends on it. These here are for, there's a range of megahertz. So you can be to 4 to 48, and that's the range it's expecting. So you put a crystal on here that will multiply out to something that will be useful for your particular application. So you do get some control for that frequency. Let's see. Oh, digitally controlled oscillators. So digitally controlled oscillators are usually they're a ring oscillator, so a ring of inverters that there's an odd number of them, and they'll circle back on each other, and they'll have a clock frequency associated with them. The challenge is these are all on, or the good thing is they're all on device. Do I have a, I don't think it's highlighted here where there's a crystal oscillator or a ring oscillator. They're all on device, but they're not as precise because you don't have the external world, a nice crystal or resonator to denote exactly what frequency it is. So less accurate, but you can reduce or increase the number of inverters in the change, and you can change the frequency. So now all of a sudden you're very agile. So I had a little project where I needed to quickly change the frequency to look at different incoming waveforms. So some were fast, where some were slow, and I wanted to adapt and use less power. So I would change my DCO settings to lower it down and reduce power and still be able to meet my my timing task. Let's see. Oh, I guess it does have it. So the STM32 you're using in lab, the AHB and the APB clocks are up to 120 megahertz, and so it only allows you're only allowed to give up a 20 or 48 megahertz clock crystal. So how do you get to 120 megahertz? Does anybody have a guess? How you go up in frequency? Yeah.
Like clock multiplication circuits before.
Yeah, they basically have a clock multiplication circuit. They call it a phase lock loop. These things are sometimes they're called PLLs, and basically they allow you to upsample. So imagine you have a faster oscillator going around, and you have a lower frequency oscillator, but every time one of these clicks goes by, you count how many of these faster clicks went by. So you say, I'm going to want to go 3 times as fast, and if I'm going a little bit slow, you increase your oscillator. If you go a little bit faster, you decrease your oscillator. So there's a way in which you can upscale a known signal source to make it, or known clock source to make it faster. There is some higher noise in this sort of thing and higher power, but it's definitely possible. And you can also adjust the frequency a little bit off of that, which is nice. So those are the PLL modules over there. Your chip also has a fairly advanced clock distribution modality or clock distribution tree where you can go and control which one of these input sources, so whether it's the 32 kilohertz or the 48 megahertz or the PLLs or the ring oscillator, you can distribute where does that signal go. Does it go to your submain bus? Does it go to your timer? You get to control all this clock distribution. Now, I don't think you're going to have to do it for your projects. You just get to know that you can do it. Yeah.
When you're writing to registers to enable clocks, is this like where you would be writing stuff?
It kind of depends if you're writing like in your peripheral, because sometimes there's registers to control that, or sometimes you're controlling here, so you're to control which clock is actually sent to a peripheral. So they have different places. Yeah, so I think at this point, using Cube ID and just clicking, this is where you just click buttons and you're praying. You're hoping that it all works out. And if you're doing vanilla normal things that the Cube ID engineers expected you to do, it'll probably work out. If you get to the point where you're doing particularly advanced things, you're trying to get like super precise timing between, I don't know, two different peripherals, sometimes it breaks and you kind of either have to go back to GCC, which would be challenging, but it's possible, or you have to kind of like really read through the documentation to get Cube ID to give you the clock distribution you want. So, not a statement that you have to do it, just a statement that it's possible to control the timing of your device. Any questions? Yeah.
So could you have multiple clocks going on at once?
Mm-hmm. Yeah, you might want to have, I mean, in our particular case, you might want your core probably going as fast as it possibly can, right? If you want high performance. But you don't necessarily have to have your peripherals going that fast. In fact, you may want to have a timer going at a very specific frequency so it keeps track of time for you in a nice way, right? So now you become in a problem where you have on one piece of silicon, you have multiple clock domains. And then there's circuitry there to make sure that you're not doing things asynchronously. You don't, as a programmer, you don't have to worry about that, but you could have that situation on chip. Okay. So next step up for that, we talked a little bit about the clock driver. Again, this is not an inherently important circuit that you have to know how it works. You just have to know that a clock driver will interface with a crystal oscillator to make a clean, nice square wave here. After that, we'll talk about the prescaler, which allows you to control the frequency of this thing, and then the counter. All right. So just think about this as there is a square wave coming in of some frequency, right? Coming into a prescaler, and then the prescaler is going to divide down by some ratio and send it to a counter. Okay, so we'll talk about the counter in a minute and how that works. The counter here is going to keep track of how many edges have gone past it. Then we have an ISR, or an IRQ would probably be a better term. But basically this is, if set properly, this module set properly, when an event occurs here, this will set off an interrupt, which you've learned about now, which will cause the main core to change modes and you can respond to this event. There's a thing here called an auto reload register, which basically says when this thing counts down to 0, what should the value that's loaded back in here be? These are typically 16-bit timers, so you could just go start at 16, FFFFF, and count all the way down and then restart, or you could put a known value in there so that you're counting down. And so the real trick of these things is to think about what's the period here. I'm going to scale that down and figure out what's the period here, and then I'm going to count that many periods with this thing. We're going to show some equations here, but if you're thinking about timer math as an equation, I mean, it's fine, but you should be able to intuitively think your way through the equations. In fact, James will be like yelling at you in the lab, like, stop with these equations. Just think about the fact that you are counting microseconds or some period, and you're counting how many of those periods. So 2 to the 16th will be how many times n period will be a certain period of time until this thing overflows. Okay, now I will give you some equations. I said I wouldn't give you an equation, and I give you an equation. That's because STM is trying to trick you. Okay, you would think that the output of this would just be like your prescaler value divided by your input clock frequency, and that would give your output clock frequency. But this is actually a register. This is a prescaler register, and they don't want you to be allowed to put 0 in there. Because if you put 0 here, say this PCS was 0, then you're divided by 0 and bad things happen. So they always, by default, add a 1 in there. So if you put a 0 in here, right, that could be the value, there's still a 1. So they're trying to protect you from yourself so that your system still operates even if you make an error. That's fine, but this equation just assumes, like logically you're saying, I have this input frequency, I want to divide it by half, so it comes out, the period is twice as long. You say, that's fine, I don't even need an equation to figure that out, but STM here as put a 1 here to force that there's a case where you can't accidentally shut the whole system off. Does that make sense? Yeah. -1, yeah. But there's no reason that 1 should exist other than STM's protecting you. And we'll walk, yeah.
Is the prescaler like a register or is it a frequency? Like
Always both. Let's look through an example. So glad you're here because I forgot that I had a demo and then you told me I will do it. All right, so this is an example of a prescaler, very basic prescaler. 4-tap prescaler, and basically each one of these is just dividing by 2. So here we have clock is coming in here fast. This is the output of 1, and here I'm divided by half, okay? Here I'm divided by 4, 8, 16, okay? So this is a very simple, this is called a clock divider, not technically a prescaler. We'll get to prescaler in a second. But all the prescaler doing, it can't count up, it can't make it faster, it can only make it slower. But you imagine that you would have a control register that would go into here, and that control register would say, okay, I want you to take this signal and divide it by 2 or by 4 or by whatever the number is. So now you have a register, part of the prescaler, that reduces the clock frequency. Is that good?
yeah, so but like when you're trying to look at like that equation,
yeah.
If it's just like a signal coming out of there, like does the like prescaler 0 be? Is that just like, I guess maybe that's just nothing then. It's just, okay, I see what you're saying.
All right. Yep, we're good. Okay, that's great. So prescaler 0 would just be this divided by 1, rather than putting 0 in here and then you have an infinite. Okay? Let me see, do I have, so I just showed you, come back. So this is a clock divider, which is literally just dividing things by half, by 4, by 8, and so on. Okay? There's another module that's called a prescaler, which is doing something more interesting, which is actually giving you a true division. It's not just divide by 2. You could divide by 5. You could divide by odd number. It's a more complicated module that we don't need to go into, but just know that there is a division between difference between clock dividers and prescalers. You have prescalers, it will actually do the division even if it's not a multiple of 2 or a power of 2. Okay. So anyways, these modules allow you to divide the clock frequency down, increasing the period of a signal. And it gives you the control so that you can hit certain timing requirements that you would need for a PWM motor or something like that. Questions? And remember, you can go through, you have questions, you can let's take this, put it in your browser, and you can play with that, okay? All right, so let's look at the anatomy of a counter. So a counter, stop here. Run. So a counter, has a clock that comes in. Remember, this could be the basic clock that comes right from your timer or your clock module, or a prescaled version. And all it does is has some control logic, and the anatomy of the timer is not, or counter is not that important. I assume you've learned that in 270. What's important is that in binary, it's going to be counting up. So this is not part of the timer. This is just a display. This takes a binary input and shows me what the value here is. So it's just a display module. And basically, this thing is a 4-bit counter, and it keeps counting up. Every clock cycle is going to increment by 1. Yeah.
Counter off and on.
Sorry.
Yeah.
Yeah. We can go turn it the other way, and now we can count down. So your counters that you'll have on your STMs can count up, count down. You can pause it as well. I didn't give that in this part of the circuit. So you can enable it, disable it, count up, count down. In fact, you can also there's more control registers built around this thing, so you could load a value into here. So you could pause this thing and say, okay, I want to reset it. So all of it will go back to 0. I can fake that by doing this. Look how clever I am. All right, so now I got 0. But you could also load in a 1 into here, a load 2, a load, or actually a load 1, 0, 1, 1, whatever value you want in here, preset it to something and have it count down. or count up, whatever you like. How does that feel? Okay. Let's see. So these can be multiple bits. Your particular instantiation of a timer is typically 16 bits, but sometimes you'll find 32, 64. It just depends on what your particular microcontroller offers. Oftentimes you'll get a count up, count down. You can hold a value, you can load a value, you can read the value out of the timer, which is super important, right? And remember, these are just memory mapped I/O modules. You're gonna have some structure like this. You have the advanced peripheral bus writing into registers. Those registers will control this and control the state of this, just like we did with GPIO pins. All right. So we're going to talk about two add-ons to the counter. Two types of control registers or logic elements that allow you to use the counter in different ways. So the two primary modes are, these allow you to measure how long something takes. So this would be a capture. How long does it take for something to happen? You see an event, you start here, and then when that event ends, you capture that time that it occurred. And then if you want something to happen every so often, like on a periodic schedule, so every time it's 2 o'clock, I want something to happen. So then you have your target, which is like 2 o'clock, and you're looking at the time going by, and you're comparing these two. When these two things equal, then an event will happen. So this is triggered by an external event, and then you look at the time. And this one is you're looking at the time, and then you do some task. Okay, so an example of a capture, kind of think about that fan example that we had from homework. So if you have a fan, you know what speed is spinning. One way to do this is to have a GPIO interrupt every time to complete its rotation. So the fact that the GPIO pin interrupts as you spin past is the capture event. And then you're just going to capture the time interval. You could do this just by having an interrupt. Well, what am I saying? The right idea, but you might want to. Okay, so if you do everything with the interrupt, that might be fine. But in a very complicated system with multiple interrupts, that could be a problem. What you can do, so you could interrupt the thing, and then, so what I guess we're saying is the interrupt could happen, then you could go and read through the core, through the APB bus, and read the value of the timer to figure out what time it is. But there's at least 12 cycles there probably, and it could be, if there's lots of interrupts, it could take even longer. So the solution here is that on this event, you will take the value, hardware will take the value out of the timer and put it into a register for you to look at later. So it's going to take that, store it for you, and then whenever the core gets to it, it can come back through the APB, read that value, and say, okay, this is the time when this event occurred. So we'll walk through that in a second. All right, so here we're back to the original timer we talked about. So you have your clock coming in, you got a prescaler, so you can control whether you want it a little bit slower or a lot slower. You have some counter that's either counting up or down, and say you want it to be AAA every single time and then count down. This will happen, and maybe you set it up so that when it hits 0, you have an interrupt service routine go off. The addition of the capture register, or it's a capture compare register, so CCR, in capture mode allows you to do something where you set the timer up, say it's been counting for a while. You set it up in main, and you say, okay, start at 0 and start counting up. And then when you see a GPIO pin, capture that value and put it into this register. So here what will happen, the GPIO pin goes high. It causes this thing, because you configured it through the registers as defined in the data sheet, to be in capture mode. And when this event occurs, it's going to take the value. So this would be, say, a 16-bit value here, and it's going to store it in here. This thing can keep counting. It doesn't really matter. But you've got this value stored here, and then your interrupt service routine will come back and read out this value later on. Yeah?
If the counter, unsigned integer overflows multiple times, doesn't that make it inaccurate to measure the elapsed time between?
It absolutely does. So that would be an error condition. Now, what you'd want to do is that might mean that your counter is going too fast for the thing that you're measuring. So maybe you have something that's going off here like at a kilohertz, right? But this thing is running at hundreds of megahertz. Then you might get that overflow event before this event goes off. So what you do is you go to your prescaler and say, slow down. I know something about the signal coming in. Slow this thing down so I don't miss this event by overflowing.
And is that done like manually, or is the?
That's by you, the programmer, manually. So you have to make the decisions, right, about how to set up prescaler, something you have to set up. The auto reload register, which controls what initial value this has to be set up. You have other registers that control this counting up, counting down. And then you have registers to control whether you're in capture or compare mode and what you should do in those cases. What other questions you got? 0 questions. Fantastic. What am I trying to show here? Yeah, okay. So imagine you have an external signal here. You can configure a GPIO pin to say, I have a falling signal and then a rising signal, and you want to figure out the time between the two. That would be an example of how to use a capture timer. So you set it up here, you let the timer go, and then you capture the moment this occurs. Okay. Let's look here first. So this is a more detailed diagram of what you would find in the STM32, or your particular STM32. There's a filtering module. This will allow you to filter out high frequency noise in basically a sublittle counter of the inputs coming in. I'll show that in a second. There's an edge detector. So now you're going to count how many edges come in. And then you have a prescaler. So you have all these different ways to manipulate and filter out signals just basically in hardware. You have the prescaler, and then you have a 16-bit counter. This is your counting up and counting down, your capture control register. You have a DMA mode that we'll talk about later in the course. And then you have your interrupt flags. You can enable interrupt, you can set the type of interrupt, and then over capture flag. I think this is if this thing runs over, to your point about overflows. You can set that up to throw an overflow signal to your core that says, hey, this is another type of interrupt. It's not just that this thing captured, it's that you actually overflowed. So if I go back a little bit, let's see. So input filtering. So you imagine you have some external signal in the world that is variable or bouncy, right, from a button push. What you can do is you can set this thing up to say, okay, I'm going to say this is your sampling clock and then internal timer clock. Oh, so this is your timer clock, but then you're going to say this is a down-converted version of this. This is a pre-scaled version. And you can say, well, I want to go sample each one of these times, and then I'm basically going to wait until it's stable transition. So here it's all varying around, so I want to see enough stable transitions before I then say, an event has occurred, and then I pass it on to the rest of the modules. So even in your hardware, you can do a little signal processing just by filtering out some of those signals. That's what the hardware, that's what this block basically gives you. Okay. So the next example would be the compare timer. So variable speed for driving a DC motor. So you want to make a signal that goes up and down for a purpose. So I don't know if any of you have dealt with DC motors, but one way you could control them is with an analog voltage. You put more voltage in, they spin faster. Lower amounts of voltage, they spin slower. The problem is digital systems are really bad at controlling voltage. And so the way they handle that is they control time instead. So instead of doing analog way, you basically turn a pulse on either max or off. And you do it quickly enough so that on average, the average between the amount of time you're on and the amount of time you're off is equal to some analog value. So if I'm 50% on, 50% off, then I'd be going half speed. If I go to 25% off and maybe 75% on, then I'm at 75%. And so this is a nice way just to use time, which is easy to control on a microcontroller, to mimic an analog power value. Yeah.
So like you use the time as when it's high, you switch to on. When it's low, it's off. So that way, like you can change the time to change if it's on or off, essentially.
What's the last part?
And you could like change how the time to change if it's on or off. Like,
okay. Well, I'll show an example of that. So we call that pulse width modulation, and it's a powerful tool for controlling external things. And most of you are probably, like anybody who's going to have a vehicle that drives around as part of your final project is definitely going to use one of these. All right. So you need, for these sort of things, you need a signal that has a certain duty cycle, so that's the percentage of time it's on. And then you need a certain frequency. How often does that signal repeat? We'll go through that in a moment. Actually, let's go through it now. We'll just go for it now. So let's see. So here is an example. What can you guys see? Nope, you can't see anything. Cool. It was a good example, though. All right. So here we have a pulse train, and I just have this clock module, and that clock module lets me control the duty cycle. So if I go and change it here, you can see that the percentage of time that I'm on got much wider, and the duty cycle is higher. I don't know what the value is. Does it say? It does not say. Okay, and then I can go all the way low here, like that. And so now I'm mostly off. And you could go all the way off. It doesn't really matter for this demo. Okay? And so the idea here is, on average, I mean, here the simulation slowed way down, and we can actually see this LED blinking on and off. I don't know if it'll work on the screen. Maybe if you squint really good, you could see some percentage of it, like it gets blurred out. So here it's kind of dimmer. It's on less. It doesn't really work. It works so well on my screen, but the refresh rate over here is not that great. So here on my screen, this looks almost on all the time. And then as I slow it down, you get to see it looks much dimmer. And so this is literally how you have those little breathing LEDs on your electronics. This is all they're doing. There's nothing fancy. They just have a GPIO pin. Oh, boy, that's dizzying fast. You have a little GPIO pin, and they're just varying the duty cycle to get you that animation effect. What do we think? Questions? Have you all seen this before? Okay. And then I guess the takeaway here is this is exactly the same signal you'll use to drive a DC motor. You just won't connect it directly to an I/O pin. You'd have to have something in between. Usually we call it an H-bridge. I'm sure there'll be some group that will present to you guys about H-bridges. And basically it just allows you to drive lots of current but still represent these pulses. So these pulses will drive an H-bridge, and then you'll be able to jump like an amp on for this period of time, an amp off for that period of time. Or sorry, an amp on for this period of time and no current on for that period of time. Okay. Yep. All right, so how does this different from before? So again, we have some clock coming in. We're going to control the frequency or how long the period is for this thing in here. This thing is going to count up, let's say. And what we want to do is have it, every time a certain value is hit, I want to change that signal. I want it to go high or low. So here what we have, we have a compare. We're going to reconfigure this register to be in compare mode. So there's other registers here that control this peripheral. And you're going to say, like, start this timer at 0 and then count up to a certain value, say 1,000. And then every cycle is going to compare. You have a comparator here that's saying, is this equal to this? And if it is, then you send out an interrupt. And there's different types of ways you can control this. You can have this directly control a GPIO pin. You don't even have to go to the core. There's this PWM module kind of built in as one of the options here. But basically, you could say, okay, if you're below 1,000, right, then we're going to keep it high. Or sorry, we're going to keep it low. And then when this thing hits 1,000, we're going to go high. And then when this thing wraps back down to 0, you go back down low, so on and so forth. So that's the way you can set the boundaries of your PWM. And there's lots of different modes for how the compare counter can work. You can force it high, you can force it low, you can force it to be frozen, and then you can have different conditions. The counter itself can be counting up, it can be counting down, you can be counting up and then counting down. So this is all that's happening here is when it hits the threshold, the auto reload value, it just is told to go back down. And so maybe you want to go and have some capture compare value here, and this is just a different way to maybe get twice as much time out of this counting setup. These are a little bit simpler. This says the auto reload at times say, so when you hit 0, then you're going to reload. The value that's going to go in the auto reload register is some value here, so some binary value, and then you're going to count down. This one is a count up timer. You're going to start at 0, and you're going to count up until your auto reload register value, and then you're going to overflow, keep going up over and over and over again. So these are different ways of controlling how the frequency of the period, let's say, or the frequency of the pulse width modulation, or the period of the pulse width modulation is with this. And we'll talk about the capture control register control the duty cycle in a moment. Let's see. There's lots of different output channels for this. So here you can have different input clocks. You have different trigger and control modes, and you have your prescaler, your counter. And then for one counter, you could have multiple capture compare registers, which is nice because now you have one thing that's counting, and instead of having a counter as a piece of hardware for every possible GPIO pin you want to go high, you can have multiple registers that do the task. So here you can say, all right, I want you to count up from 0 up to 2 to the 16th, and then at some value, say 1,000, I want you to do a task. And then maybe 2,000, 3,000, 4,000. So with one counter, you can reuse it 4 times. And then these will go through and go out to an output channel or output controller, and these eventually would go to a GPIO pin. So with one timer, you can control multiple PWM signals. Questions do you have? Okay. So we already gave the example here of what pulse width modulation is, at least the intuitive example. How you can control this is here you have some reference signal, and all this reference signal is saying, okay, when this value, so this is supposed to be counts on this line, and this is time, and so here 1, 2, 3, 4, 5, we count up to some reference signal, and when that reference signal goes high or hits the same value, then we can have the pulse width modulation go high, and then when it reflows, we go back. So here's a way to control to set up a pulse width modulation, and so the time that goes up is the period, and then this value here represents the time this is. So all you have to do is change your reference signal up and down, and that will make this go wider or lower. All right, so let's walk. Any questions so far? Yeah.
Wait, so the counter is able to up the voltage in the next linear format like that?
The counter is able to up the voltage.
With the first thing. Like that's just like
these are steps. Sorry, we're zoomed way out. And so this is counts, not voltage. So this is the counter has a value 1, 2, 3, 4, 5. And that's a fair criticism. This is a better example here. So it's the same sort of diagram. We have a counter that's going to count up. It kind of has meaningless if you only have 6 steps, but whatever. That's what it is. So here, auto reload register says, okay, you set your counter to count up. When it hits 6, then it's going to overflow, and then start at 0 again and go. So the auto reload register. All right, and this is time, or this is clock. So here's the periods. So you can go through and say, my auto reload register is essentially controlling the period of this waveform that's coming out. It'd probably be better to say that. So yeah, that's the auto reload register, great. And then the repeat control timer, this doesn't really come up that much in these examples, but it's something that's going to come up in lab. So this tells you, should you keep repeating over and over again, or should you stop after one cycle? And so that's nice if you just want to send out one pulse, well, you don't want to have multiple pulses coming out, so you have a method of controlling that. Okay. Let's see. So here the period is basically 1 plus AAR times the clock period, because these registers need the extra 1 in them, and so now you can go figure out what the period is based on your number of clock cycles. Let's see. So countdown mode, similar. You can start at your AAR, and then count down to 0. You have the underflow event, which brings you back into AR. So basically, you have that timer module, and the AR is being put back into it on these underflow events. And here's another way to come up with your period, either counting up or counting down. Yeah.
Can you change AR on the fly if you wanted to?
Yeah, whenever you want. So in that case, you're not guaranteed that this period will be right. So you could like change it here, and then bad things could happen. But then you might, from an application point of view, say, does that actually matter? And I think on some of the timer modules, you can wait until this next event occurs. So you can tell the auto reload register, don't reset the time until you get, in this case, a underflow event, and then so that way you don't have this kind of run pulse that makes weird things happen. And just an example of a center mode where you count up, it gets up to your AR and then counts back down. So the overflow event here causes it to change direction and counts back down, and this is going up and down and up and down. You may say, why is there so many modes? It's just because it just gives you the flexibility. The cost for STM to put all these modes in the microcontroller is pretty minimal. It's a little bit of extra logic, but it gives you a lot of flexibility because typically the joke is you can never run out of timers. I forget how many timers there are on your chip. I think there's like 24 or something. And it is literally possible that that's not enough for some applications because usually there's a lot of time-dependent things you want to keep track of. So they're just giving you flexibility. So let's talk about how to generate the pulse width modulation. So we talked about how to get the period set up. How do we get the pulse width set up? So here you're going to go and have your you're in up count modes, your auto reload register overflows, and then counts back up again. And now you're going to have your CCR, so your capture control register, say it's 3. It's constantly comparing. Is the count on the timer 3? No. Is it 3? No. Is it 3? No. Is it 3? Yes. If it is, now take some action. And you would have a register that sets some action up. Yes?
Is there any worry about the sub-latency to compare between the CCR and the current counter?
You mean the latency of the comparator itself? Yeah. No, because we can make those things relatively fast. And so the designers of the hardware are telling you, hey, that propagation delay through that comparator is smaller than the fastest clock cycle that you could put through this. We're just going to assume that STM did a good job. If they do bad things, it'll be interesting. That's a good question. All right, so what do we got? We got, so anyways, we're going to compare it. It's it's equal to that value. Now let's do a task. What's that task going to be? In this particular case, you have to configure the timer output modes, whether it should be positive edge or negative edge. But here, we had an edge come in, and that has caused our output signal to go low. Then when we underflow or overflow here, then we're going to transition. It's going to go back up. So now we have a oscillating waveform, like a square wave. And by controlling the CCR, if I pull it down to 1, then this thing is going to get much wider. If I put it all the way up to 5, then it's going to be very narrow. And you can work yourself through the math to figure out how all that works. Again, the auto reload register, because STM is trying to help you by always guaranteeing there has to at least be a 1 in here. They never want you to accidentally be able to put a 0 in there. Okay, so now you can go through and calculate your duty cycle and your period. Yep.
Where does the prescaler come into play here? Is that when you just like don't want to use a clock and you want to use like a different signal?
Prescaler is a version of your clock. So it's not like you don't want to use a clock. It's just maybe that clock isn't the correct one that helps you with your application. So we had a previous question of what happens if you're overflowing. In that case, what's probably happening is that your clock is going way too fast to measure those slow human things, right? And so what you'd want to do is you use your prescaler to slow down that clock so that you have enough ticks in your counter to measure the thing you're trying to get to. So a lot of what's going to happen is we're going to give you a problem that says, hey, there's an event that happens at this frequency, And now you have to be able to set the period at a certain amount so to guarantee you're going to hit that event. And then we might also say we want to have a certain resolution, right? Like here's how fast your time's got to be. Well, then you might change your prescaler to have a certain step width. Yeah.
Is there ways we could like do CCRs like below like 1, 2, like 3 states?
There are 3 states?
Like for the timer.
Well, CCR, for the making a decision in CCR, they always say it's going to be greater than, or is it less than, or greater than or equal. So there's no just equal state. Does that answer your question?
I was wondering like if you could have like multiple values like the CCR, like so you wanted to like have different outputs.
Oh yeah.
Between like if it's less than this, greater than this, but also less than this one piece.
Yeah, I have an example of that coming up. And that's the multiple output modes. So yeah, we'll talk through that example. Here, just demonstrating that the logic could be inverted. Right, this is the difference here is this is mode 1 up in the corner up there. Mode 2 allows you to go in the opposite direction. And I guess the takeaway here is now the duty cycle is just basically counted differently, right? Before the duty cycle was 3 over 7, and now it's 4 over 7. And that's just because we changed our logic about what was logical high and logical low. Here's just an example of we've gone and moved the CCR to 5, therefore this duty cycle has gotten smaller. Periods stay the same in this example. Here the periods gone twice as long, right? Because we had to count up and count down, and now we're saying that the CCR is 3. So now the CCR has this up state, and then when you're coming back down, so internal logic says when you're advancing, then the positive edge or for your advancing, you go from 2 to 3 on this edge. Then we're going to make this a high signal, and then when you're decrementing, we're going to have a low signal. So it's just a slightly little bit of different logic. And we're not going to make you memorize the modes on an exam or homework. Well, homework, I don't care. You have reference sheets. But we're not going to make sure you remember which mode. It may be enough to say, hey, this thing has these 3 modes. There's a description about what each mode does, and then you have to go and pick which one you are going to use to accomplish a certain goal. I feel that would be in bounds for our exam. And again, this is just showing here I can go change this duty cycle, right, proportional to where my CCR is. Now back to your question. If we look at the larger block diagram for capture compare modules, for the compare, you have a timer, or you have your clock, you have your prescaler, you have your counter, and now I can have multiple registers for capture compare 1, capture compare 2, 3, and 4, and then those can be configured to have an output channel sent to a GPIO pin. And that allows you to do things like this, where with one timer set to some AAR, you can have 2 different CCRs with different values, and now you can generate different signals. So here's the example of the CCR3, CCR6, and now you're able to generate 2 pulse width modulations using one timer. The trick is, when you're thinking about all those things you need to control, you're going to want to make sure that the period for both is reasonable, right? You can't dynamically change the period for both events from here to here, but you can certainly change the duty cycle for each. What questions do you have? Okay. Sure, right line mode. Okay. Talked a bit about this. Yes. Somebody asked about synchronous updates for your auto reload register versus asynchronous. So synchronous updates wait for the underflow event or the update event, this is overflow or underflow, to occur, where asynchronous events don't. So the only difference is that asynchronous events is going to guarantee that, say you had a certain period or a certain duty cycle, that, and you changing to a larger one, that there's a clear delineation between that. You're going to go from one duty cycle to another one. If you do it asynchronously, you could have this one runt, really small duty cycle or kind of a long duty cycle. So just knowing that these 2 modes exist can help make things work better. This would come up, say, if you had a servo And normally you have a 1 pulse width modulation, and like this way is lower and this way is higher, and you just happen to upload asynchronously, and just for 1 cycle it twitches this way and then it twitches back, right? Where you really want to go up, but because you just happen to be in the wrong part of the duty cycle, the asynchronous method, makes you a very short pulse for a second. And that would just be a small control error, not that big a deal for many applications, but it gives you the option to control that. All right, so now you guys are getting to the point where you should be becoming familiar with the data sheet. So the devil's in the data sheet, and it's coming to the point where it's your expectation, or our expectation, you're gonna read through the data sheet when you don't know what registers do, what the exact value is, and what values to put in there. That is essentially where we're moving to in the class. What else is there? Yeah, there's lots of different ones. So you have main enable, different control registers for enabling capture compare on different channels and deciding what mode to run in. And here's like the full diagram of, I showed you the toy diagrams before. This is more of a typical block diagram for the advanced control timer blocks. That these are in the peripherals. This is not the system clock. But you can start seeing some of the same things. We have this edge and filter detection. You have pre-scalers. So this is pre-scaling the signal coming from the edge filters. You have capture compare timers. You have output paths here. You also have clocks coming in from your main timer. So you can go and control all the clock speed, and you can control the pre-scaler that goes to your counter. So there's pre-scalers for your input signals, kind of more rarely used. You're definitely going to use a pre-scaler for your input clock edge. You have your counter here, and then you have multiple capture compare registers. In this particular case, you have 6 for one counter. You have an auto reload register, your repeat register, and then your interrupts and all these other output controllers. Okay, so you should more or less be able to read through this block diagram, at least to know, like, oh, there's actually 6 here, and here are. You can look through here and say, oh, I didn't realize there was a pre-scaler, or I could get signals from different locations. All right. Sure. Any questions? Let's do a problem. So your job is to set up a pulse width modulation with the specs provided. You guys got 16-bit clock source, 16-bit timer, and your goal is to make, let's see, a 10 millisecond period with a 10 duty cycle. Yeah. What happened to you? They didn't like you? They said no. They said he had to sit by himself. You guys had to sit by yourself. You didn't even get a seat. Yeah. You guys got more? All right. There you go. Thank you. Here, send those down just in case.
Sure, yes.
Everybody get one?
Depends on how much
Go.
they are. Ah, shit.
All right, so just to be clear, you're trying to create this waveform. All right. 10 millisecond period with a 1 millisecond duty cycle. You're given a clock at a certain frequency. 16 megahertz does not divide nicely. You might want to pre-scale that down by some value so you can do your division nicely to get these sorts of signals out of that.
And then after that,
The monitor, I said yes, go for it, as long as we have space. I just want to confirm that we have space. Chairs, do we really need?
I mean, there's like half listed in
To 10, you could be more precise and give yourself.
How many, but it's just gonna
I wasn't-
clog up the workspace.
I wasn't thinking about getting chairs. I would like some chairs, but like that was not my thought. I'll check out this problem.
Answer seems overwhelmingly horrible.
So we need the PS.
This counting whatever. To be like this is the CCR value.
1 over 16, figure out what that's worth.
This goes high.
Definitely on it's going to count how many of those periods of assumption say 16 is not divided.
We just need to plug it into given the period.
Is high over is larger.
Where are we going to?
Isn't it? Oh yeah, 3.
What's the big goal?
What CCR values do you need to achieve a PWM with a duty cycle of 10% and a period of 10? So
Duty cycle.
how does duty cycle be in percentages?
I think it's just with the correction, so just saying 1/6 is like. Duty cycle of 1/10 is equal 1 minus r over a r. We do it this way. Do.
I'll teach you things.
But to get the frequency, you just have to convert it to clock period. Yeah.
Do we know this CCR is 3? Just
I think you have freedom, right? It's Android as long as everything else lines up.
Wait, wouldn't it have to be 15 then?
It's 1/9.
Period went by, 2 periods went by, 3 periods went by.
Prescale would be the
Yeah.
It would be 16.
Yeah, 10 to the -6.
Millisecond. Your prescaler is a way to do that.
I think you gotta make it the clock period. You know, you can figure out. And it just 1 over period.
There are 30 over now.
When you get the A so then it's 1 over 16 megahertz. Megahertz is 10 to the third. It's 1 million.
Yeah, I think at 90 over 30. Over 9?
Yes.
I got 10 times 10. Maybe clock period is 16 megahertz.
On these slides.
It's on the previous slide.
What?
You went over this.
This is just
Clock period is be 1 over. Oh, for clock period, I got 9.
I meant milliseconds. Then you get 1 equals 2 times A.
I didn't say what's the three options.
Or that'd be 10 times 10 to the negative.
No, it shouldn't cancel out. Oh, wait, no, milliseconds. Because it's 16.
For the
Our R is in.
Can you make a tour? Oh my god, I can't read my
divide by 160.
You grade Q5.
2 is select.
Hundredths of a millisecond.
Just prescale it by.
Nice number.
I read all the slides from last time.
But then how do you set the prescaler? Find the time of prescaler.
For this, 10 milliseconds, right? Should I convert that to seconds or like what's like the basic?
I think you need to -1. I'm still making sure this is true.
And skill.
To get ARR, you -1.
-1 over 16 million.
That's what I'm talking about.
Oh.
For the 312
milliseconds.
actually.
And then compare this, then you can scale it like a 1-to-1 scale, or you convert this to
What you're
megahertz.
gonna find out is that
TSC gave you a new clock. R is what? It's greater than a number, so it's
Over 16 times the full size.
Yeah, which R simplify is just
It's just fine.
much of it. It's high.
It's 1 over 6. It's 10 to the negative 6.
1,000.
Over 10 megahertz or whatever.
no, it's 1 over. It's
1
a
over
ratio.
100.
It's a ratio. It's not 1 over 10 megahertz. It would be 15, let's say.
What I think.
And just bring 16 to the numerator.
16 cents, 1 megahertz.
Yeah.
Okay, gotcha.
Did we do this? Two numbers that are the same and saying that is how they got it. Modulation.
We don't have a lot of time, I have 0 time, but these will be, I'll post these slides. Basically, the trick is there's multiple ways, there's multiple prescalers that allow you to get to this value, right? So you're at 16 megahertz, and so really, it's not frequency you should be thinking about, it's periods, right? So you invert that and you get the periods, and then your counter counts how many of those periods have gone by. And you're trying to count up to 10 milliseconds. That's where your AAR is supposed to be, or ARR is supposed to be. This is supposed to be equal to counting up to 10 milliseconds worth. And so 1 over 16 is not a nice happy number, but if you divided it by 16, then at least you get a number that's a little bit nicer here. And then you're gonna set your CCR to be some number of those units, these periods you're gonna count up. So here's one set of solutions, because you can have multiple there's multiple prescalers that could work, but I said, okay, let's make it easy. Let's divide this by 16. Now remember, ARM is trying to trick you. Don't let them trick you. You want to divide by 16, but it's 1 plus whatever the value you put in your prescaler. Okay, so now that gives you 1 megahertz. And then you're going to go through and do the math to set up your pulse width, like how many ticks have to go by to get to 1 millisecond, or 100 milliseconds. And in this particular case, it was divided by 2, because it's scaled up and scaled down. And then you're gonna go through and figure out what your CCR is. So I know we don't have enough time now, but just work through the math, you'll find the solution to get through it, and we'll go through another problem to find it. Okay? All right, thank you. Turn in your worksheets. I mean, this is gonna be in the slides, but if you want to, you can take a picture of your worksheet as well.
I think I'll have hot tub when I go.